Hello everybody, welcome to this video giving an introduction to areas of surface of revolution. So in this section, the pictures are going to be kind of similar to back when you studied volumes of revolution in Calculus 1, but rather than finding the volume of the inside of a region, we're going to be studying the area or the surface area of the outside or of the boundary. So let's get started. So as normal in calculus, we have to represent things somehow, and the way we represent it is using functions. So y is equal to f of x. That's a curve, and we rotate it about the x-axis. We get some kind of 3D shape and we want to see how to find the surface area of the boundary of this 3D shape. So we're not finding the surface area of the ends here, but we're finding the surface area of the boundary as we rotate the curve around the axis. So if you kind of imagine that curve spinning around the x-axis, it's going to give some region in 3D, and we're trying to find the surface area of the boundary of that. So how should we do that? And as usual in calculus, we have a hard problem and we study it by splitting it into simpler problems, understanding those instead, and then somehow using it to get to what we want. So let's first look at a special case, which is a so-called circular frustum. And all that means is it's a circular cone with a bit cut off the end. So here is my big circular cone, and then we cut this bit off the end, and you get something that's called a circular frustum. So there are two different radii. There is the radii of the circle on the bottom, there is the radii of the circle on the top. So let's call those R1 and R2. And then there is the length of the hypotenuse, let's call it L. And you can show using just using a few steps that the surface area of the boundary of this, so not including the top and bottom, but including as we rotate this hypotenuse around, that the surface area of that is 2 pi r times L, where here R is the average of R1 and R2, and L is just the hypotenuse that's in the picture. And how would you get this? For instance, if you forget about the circular frustum and you just start with a circular cone, so including this piece at the top, if you cut it open along one of the edges, imagine you have a circular cone made of paper or something like that. If you cut it open and unravel it along one of the edges, you'll get a sector of a circle. Okay, you know how to find the area of a sector of a circle. You have to do a little bit of algebra to write things nicely. So that will give you the surface area of a circular cone, and then you would have to do the surface area of the large cone minus the surface area of the small cone. It will give you the surface area of the remainder, which is this circular frustum. So I'm going to skip over those steps because they're not very calculus-like, but that's how you would do it. So let's see how we can apply this. So right now, this does not seem to answer our problem at all. So here's a general picture. We have a function y equals f of x. We are rotating about the x-axis. So this is the picture from 2 slides ago, except I draw some extra things on in red. So what are we doing? Well, our function is not a straight line, and it's not very well approximated by straight lines. But like back when we looked at arc length, if we chop up into enough pieces, these little intervals, x0, x1, and so on, we chop up into little pieces. On each of them, we approximate the graph by a straight line. Say here, I have a little interval. Instead of having a curve, I approximate by a straight line, so on. Similarly, in the middle, we approximated by a straight line, and at the end. And I didn't draw everything on because it would make the picture impossible to understand, but you could do that everywhere, approximate on little intervals, approximate the function by a straight line. And the point then of having these straight lines is that as you rotate these straight lines, each individual straight line around the x-axis, these give little circular frustum, so the little shapes that we talked about on the last page. Of course, they're now on the side rather than before they were, here is the outer radius, for instance, or here is the lower radius, here is the upper radius, and so on. So they're just rotated around. So presumably we can then find the radius, the lower radius and the large radius in terms of the function, in terms of the xi. We can find this, this slant height in terms of the function, and we can use that to get an estimate. So here are the steps. We approximate our curve by a bunch of small line segments. We rotate each of these, we get a circular frustum, as we said. We add their surface areas, which now we can calculate based on the stuff in the previous slide. And then, okay, we take the limit to get the exact surface area, right? As we chop up into more and more pieces, these lines are a better approximation of the shape of the curve. The frustums that we get are going to give better and better estimates of the surface area of revolution. In the limit, we get the true answer. Okay, so that's our derivation. Let's move on to the formula. So in the kind of model case, which is maybe the most common case, suppose we have a function y is in terms of x, and we want to rotate about the x-axis, which is what we saw in the pictures just now, then the surface area is the integral from a to b of 2 pi y square root of 1 plus dy dx squared dx. And here, even though there is root of y, remember, we're going to want to write this in terms of x using our equation y in terms of x. So we're going to take this formula, we're going to work out dy of dx and whatever, work out the square root as we did in the arc length section, And then we're going to take the y here and replace it by whatever it is in terms of x using our formula. We're going to get something all in terms of x, and then we integrate it, we get the area of the resulting solid, or the surface area. Okay, so here is an example. Let's find the surface area of the surface that we get by rotating this curve, y equals the square root of 4 minus x squared, about the x-axis. So all we are going to do is take our formula and write out all the terms. So we are going to need to find dy dx. Okay, here dy dx is from using the chain rule. Outside is u to the 1/2. Differentiate, we get a half u to the negative 1/2, where u is this inside. And then we have to multiply by the derivative of the inside, which is going to be minus 2x. Okay, we multiply all this together. Here is our dy dx. And then we are supposed to get we're supposed to integrate 2 pi y squared of 1 plus dy of dx squared. So before integrating, let's try to write it out and see if there's anything we can simplify with algebra. So 2 pi y, of course, we have to replace the y by what it is in terms of x. So y in terms of x is the square root of 4 minus x squared. And then we have the square root of 1 plus dy dx squared. Okay, 1 plus dy dx squared. Dy dx squared becomes x squared over 4 minus x squared. So this is just writing out all the terms in terms of x. And then, okay, we want to see if we can simplify anything. So if we combine our square roots, remember the product of square roots is the same as the square root of the product. If we take this 4 minus x squared into the other square root, we have to multiply the 1 by 4 minus x squared, which gives us this 4 minus x squared. And then we have to multiply 4 minus x squared by x squared over 4 minus x squared. Okay, and some magic happens and the 4 minus x squareds cancel, and we're just left with x squared. Then we have 4 minus x squared plus x squared. Of course, the x squareds cancel. Square root of 4 is 2. So this turns out to be 4 pi. Okay, so that simplifies quite a lot. Almost like this was chosen for that particular reason. Okay, and then we just have to integrate it, right? This was exactly the thing we were supposed to integrate. And we're supposed to integrate from -1 to 1. 4 pi, okay, we get 8 pi is the answer. So we managed to find the surface area of our region. Okay, so let's look at also some other cases. So here, we were working y in terms of x, and we were rotating about the x-axis. So we might also want to consider or be forced to consider other possibilities. So more generally, we have y in terms of x or x in terms of y, and we have to rotate about either the x-axis or the y-axis. So if we have two options for each of them, that's going to give four possible formulas. So how do we choose the right formula depending on what we're doing? So if we rotate about the x-axis, which is what we just did and what was in the formula 2 slides ago, then we're going to be integrating 2 pi y ds, where ds is something we have to use the right formula for in a second. And if we rotate about the y-axis, then we have to do the integral of 2 pi x ds, where ds again is going to come in a second. So rotate about the x-axis, we're doing 2 pi y ds. Rotate about the y-axis, we're doing 2 pi x ds. And then we also have to think, do we have our curve y in terms of x, or is our curve x in terms of y? And based on that, we're going to use different formulas for ds. So if y is in terms of x, then we are going to want to replace ds by square root of 1 plus dy dx squared dx. And if x is in terms of y, we're going to want to replace ds by square root of 1 plus dx over dy squared dy. Okay. So if you're given a problem involving surface areas, look for which axis. Based on that, you'll choose the right formula from the first part. And then do you have x in terms of y or y in terms of x, or if neither, which is easiest to rearrange for? And based on that, you replace ds by whatever it is in the second part, and then you'll have your formula. And you want to make sure that everywhere you have things in terms of, before you integrate, you should be working just in terms of one variable. So if there is a y here and you are supposed to be working in terms of x, you are going to want to replace that by whatever it is in terms of x. If there is an x there and you're working in terms of y, you will have to replace the x by whatever it is in terms of y, using the equation of the curve you have. Okay, so let's see an example, and then we'll do some more examples in class. So an arc of the parabola y equals x squared from 1, 1 to 2, 4 is rotated about the y-axis now, so that's different from before when we were looking at the problem with the x-axis. And we want to find the resulting surface area. So we look for the two important things we have. So y is in terms of x, and we are rotating about the y-axis. So rotating about the y-axis, we started with the integral of 2 pi x ds. And now we have to choose the right formula for ds. We're working y in terms of x. So y in terms of x means that ds is supposed to be replaced by the square root of 1 plus dy dx squared dx. Okay, now we just put those together. So we are going to get the integral of 2 pi x. ds becomes square root of 1 plus dy dx squared dx. This is going to be our formula for finding the surface area, and now we just have to plug everything in. So since we're integrating with respect to x, the limits are going to be x values. So we are going to be integrating from 1 to 2. Then the 2 pi x piece, notice now that because we have x and we are integrating with respect to x, we don't have to do any replacement. So we only have to replace the first part if we are switching. So here we have the x just stays. But okay, now we are supposed to fill in the dy dx squared plus 1 square root. Okay, y was x squared, dy dx is 2x, dy dx squared is 4x squared, and so on. So here is our integral setup. And then you could do, for instance, u equals 1 plus 4x squared. You would turn it into a user problem, change the limits, and so on. Those are a sequence of steps from Calc 1, so I'll skip those, but in the end, here will be the answer. Okay, so we talked about how to find the surface area of a region or a surface of revolution. And there are two things to look for in the problem. Are we rotating about the x-axis or about the y-axis? Is y in terms of x or is x in terms of y? Based on that, we want to choose things so we have the right formula. And once you pick the right formula, depending on the cases, it's just a case of plugging everything in. Okay, thanks everyone. See you next time.